Okay, so today we are going to continue talking about thermodynamics. We're going to be talking about this concept called Gibbs free energy. Okay, so here is our equation for Gibbs free energy. I'm going to write it down and then I'm going to explain it because it needs explaining. So let's start with the things that we already know. Delta H is called enthalpy, or H is called enthalpy. Delta always means change in. And if we have that little degree symbol, it means that we are running the experiment at standard conditions. So if you see that, that means you're at standard conditions. Standard conditions is not the same thing as STP. But it does give you a value for temperature and pressure. So standard conditions means that you have 1 mole of a substance. Your pressure is 1 atm. And what's different than STP is that at standard conditions, your temperature is 298 Kelvin, which is 25 degrees Celsius, which is room temperature. So most of the time when we are working with gases and the ideal gas law, we're running those reactions at STP, where the temperature is 273. That would be 0 degrees Celsius, so at water's freezing point. But that's practical for gas reactions. It's not always practical for chemical reactions because we're probably conducting them in our regular lab, and that's at room temperature. And so that's why we would use this. So if you see the little degree symbol, that's not a degree symbol in this case. It is telling us that we are at standard conditions. Why would we want to use standard conditions? So that our data can be compared to data from other scientists. Another thing that is known to us, T equals temperature. And most of the time, we need to be using Kelvin as our unit. That really depends on what unit you're using for the other variables, but it mostly always is Kelvin. We learned last time that S stands for entropy. And so delta S would be change in entropy. Remember that entropy is disorder, and entropy is a way of measuring how your reaction is changing in its disorder. So if you are a reaction that looks like a combination reaction, your delta S would be negative because it would be non-spontaneous. And if you had the opposite, delta S would be positive. The reason for this is because here disorder is increasing. You have a greater amount of particles. So this would be like going into, you guys have siblings, right? Have you ever gone into your brother or sister's room and just trashed it? Just gone into their room and thrown their shit all over the place? My sister and I used to do that to our brother. And then he would always cry about how the girls trashed my room. It was a thing. You've never done this? Oh, well, I'm sorry for you. So here order is increasing because here we're making things tidier. We're combining our substances to make one product. Here you're my sister and I trashing Craig's room, and so your disorder is increasing. Remember that in order for a reaction to be spontaneous, we want that entropy to increase, even though that's counterintuitive in our minds. I don't think Craig was happy that we trashed his room, but if it was a chemical reaction, he would have been. So then what is G? This is what we call free energy, and it's named for the scientist Gibbs, who was the first to really postulate this idea. And so we really define this free energy as the maximum energy available to do useful work. So this concept is a little bit confusing to us because we think about work in different ways in the human brain. We think about work as getting our work done. And so completing a task or finishing our homework or something like that. In science, we don't think about work in that way. We think about work that is done as traditionally. So if we're thinking about work in terms of physics, it's a force over, like a force is applied over a distance. We talked about this once before. And so usually pressure and volume in chemistry is how we define what work is. And so if there's a change in volume of a substance, then useful work is done. What does that mean in order to change the volume? It really means, can the reaction progress? Can products be made? So, in other words, can products be made? That's the work of a chemical reaction. Which makes sense, because if you made a chemical reaction, if you wanted reactants to combine together to produce products, you would want that whole thing to progress. You wouldn't create a restaurant and put menu offerings on a menu if you didn't want them to sell. Okay, so let's go back to our sign conventions and just review this. This is so important to know how to think about what the numerical value of these variables mean. In order for a reaction to be spontaneous, delta G has to be negative. Spontaneous reactions are reactions that can take place on their own without any energy added to them. If we look just at the enthalpy of a reaction, the reaction is spontaneous with respect to enthalpy if that numerical value is also negative. The opposite is true for entropy. We want the sign of entropy to be positive in order for that reaction to be spontaneous with respect to disorder. And then obviously the opposite is true here. If you can memorize and understand what is in this box, this will be of great use to you on your AP test. But now let me write down the formula for free energy here, and let's talk about this, because this concept, the sign conventions, is also built into the math of this equation. So if we want this number to be negative, the reason that we are subtracting this term here, the T delta S, is so that you're turning this positive sign. So if you're always using Kelvin as your measure of temperature, temperature will always be a positive number. It's not possible to have a negative temperature value using the Kelvin scale because the lowest possible temperature is 0. And that's absolute zero, a theoretical construct. And so whatever then is the sign of entropy is going to determine the sign of this term. If we want Gibbs free energy's value to be negative, And so like delta H can be anything, but let's just say for this, for all intents and purposes, for right now, that it's 0. That would never be a possible thing unless we had pure elements, because other things, when they form, heat has to be involved somehow. But because elements exist as how they are, their like elemental form, their formation enthalpy is 0. Okay, so let's just imagine we're talking about something with this sign, or this number is 0. So if delta S is positive, that would mean that the reaction is spontaneous with respect to entropy. What would be the sign of this whole term in the math then? It would be negative, which would give you a negative delta G value. So the fact that this column is true is the reason why in this mathematical formula we have that negative or that minus sign, because we want delta S to be increasing in order for the reaction to be as spontaneous as possible. Yes, ma'am?
So if delta S was negative, it would be
Positive, right. Yes, yes. And so if that were true, if we still want free energy to be negative because we want our reaction to be spontaneous, and delta S is negative now, that means that this whole term would be positive. This number would have to be a bigger negative number than whatever that term was.
And the T is always positive, right?
It has to be, yes. Yep. And that's really the beauty of using the Kelvin scale, because you'll never have a negative number. It's not possible. That's the third law of thermodynamics. So, how do we know if a reaction is spontaneous or not? Some reactions are spontaneous. Okay, so the overall reaction, you're going to look in this column. And so if you were just asked, is a reaction spontaneous? Here is this value. If delta G is negative, yes. Delta G is positive, no. But in order for this number to be negative, other things can be true. So you can have a reaction that is non-spontaneous with respect to enthalpy, as long as it is spontaneous with respect to entropy in a way that will outdo it. So, for example, if you want this number to be negative and your enthalpy of reaction is positive, this number, this term, the T delta S term, has to be a more positive number than that enthalpy to outweigh the fact that it costs heat energy to do the reaction. And so I suppose you could think about this in terms of like effort and reward. Although I don't have an analogy like right at the tip of my tongue to explain that to you. But have you guys taken economics already? Have you learned about opportunity cost? Yeah. The opportunity cost of something is so if something is special that only comes once in a while, even though it might cost a lot of dollars or time, it might be worth it in the long run because you'll never have that chance or that opportunity again. And so you might have to do a little bit of sacrifice in order to make the thing happen. The same thing is true about chemical reactions. So you might have to sacrifice a little bit in the entropy side if you can make things work with enthalpy. Let's do a couple of examples of how to actually make this work mathematically, and then hopefully that'll help us to put some concrete terms together. Okay, so how to calculate delta G. Okay, so you need to first calculate delta H of the reaction. And we can do that simply by finding the sum of the products minus the sum of the reactants. We've already done that. We did that when we talked about Hess's law. The second thing that we need to do is calculate the delta S of reaction. And we did that last time. That was what you spent your homework doing. It's calculated the same way. How do you do that? You look up the entropy of formation. You multiply it by the stoichiometric coefficient of each one of those substances. And it's always sum of products minus sum of reactants. The tricky thing about this is that if you look in your appendix, the units must be converted. So if you look in your appendix, you're given this information as joules per Kelvin per mole, and you're given this information as kilojoules per Kelvin per mole. Great days. So one of them has to be converted to the other because you cannot add two different units. So when you get this answer, I would just recommend calculate delta S reaction and then divide by 1,000. That'll give you kilojoules, which is what you had from enthalpy. And then you're just going to be able to calculate delta G then. You need to know the temperature that you're running your reaction at, but if you're using the standard conditions, it's always the same. T equals 298. So here's a little thing that you can think about. I know that I think I put some MCQ questions together like this. And every single practice test I've seen has questions like this. To make delta G as favorable as possible, so in order to make it the most favorable, we want largest negative number. There are a couple of things that you can do. Now, you might not be able to control enthalpy, but you can manipulate your temperature of your reaction. And so that gives you a little bit of freedom. So, if delta S is positive, in order to make delta G as negative as possible, you want T to be at a high temperature. Why? It'll make this number the most negative it can be. So if entropy is positive, if your entropy is increasing, run your reaction at your highest temperature allowable. So heat it up. The opposite is true. If your entropy is negative, you want to try to mitigate the fact that you are losing disorder or you're gaining order. And so you want to use a low T. That won't change the sign of this term in your mathematical equation, but it'll mitigate it. And so if you're running this at as low a temperature as possible, and delta S is, even if it's a really big negative number, you can take care of that by just making T smaller. So you might not be able to do anything to change delta S and delta H, but you can manipulate temperature. And so if you are able to manipulate it enough, you might be able to turn a non-spontaneous reaction into a spontaneous one, depending on your situations. Right. I'm going to give you some homework problems to practice this, if I can find where I put them. And you're going to need your book because you need that appendix. Yes, of course. Yes, of course. I'm going to pause this. Okay, so we are looking at homework 9. Let's try to do some of these problems so that we can get a firm grasp on how to navigate through this. It's not difficult, but it is tedious. Okay, so you'll need the appendix. Is it A19, Logan? Yeah. You'll need A19. Let me just see. So what we need to do in question number 1 is to start by making a chemical equation. So it says, using the values for delta HF and S found in the back of your book, calculate the standard molar free energy of formation, delta GF, for each of the following compounds. So that means we need to be able to write a chemical equation for how compounds form. So it'll always be the elemental form of all of the elements in your compound that are your reactants, and then your product is that substance that you're given in the problem. So the more complicated your substance, the more elements exist in your product, the more elements will exist in your reactants. Okay, so what is the elemental form of carbon, though? It is graphite. Graphite is more stable than its other solid brother, diamond. That was the most heartbreaking day I had in college, was when I learned this thing. I don't know how I never learned it before, but it was a little sad to me. Hydrogen exists as a gas, but it is diatomic, so H2. And then here it tells me that we're looking at methane in its gaseous form. Okay, so the way that I set my problems up, I just make a list of all of my data and then I do the math later on. You can choose how to do it however you want.
Do we balance hydrogen out?
Oh yes, we better do that. Thank you, Marina. Because that'll be important later on if you don't do it. Okay, so graphite, my delta HF for my elemental forms had better be 0. Otherwise, you're looking at the wrong form of it. So that's how I know not to use diamond, because even though it's got a 2 and that's a very small number, 2 is not 0. And then S for diamond graphite is 6. For hydrogen, H2 gas, is 131. But thanks to Marina knowing what to do and balancing our equation properly, we know we have to multiply that number by 2 because that's its stoichiometric coefficient. CH4's delta H is negative 75, and its S is 186. So right off the bat, I am confident that this reaction is going to be spontaneous because I have 2 spontaneous terms in my products. Although I do have to do the math to make sure. So delta H of formation would be the sum of products minus the sum of reactants. It'll be negative 75. But now look at your unit at the top of the column. It's kilojoules. Kilojoules per mole. So now I want to do the same thing for the delta S row. And so that's going to be a little bit trickier math. It's just going to be 186 minus 2 times 131. I'm going to put that in little brackets. Don't forget the plus 6. It's a small little contribution, but it's a contribution nonetheless. Okay, super. Now my unit there is joules per mole per Kelvin. So I need to account for that and divide by 1,000 straight away. So you should get negative 0.082. If we are running this reaction at standard conditions, T will be 298. And so now that I've got all the variables or the numbers I need for my variables in my equation, I can just plug it in. Divided by 1,000, dummy. So you should get negative 50. Your significant figures, you would not have any decimal places because there are no decimal places here. But you can really consider that the numbers that you take from the back of the book to be exact numbers. And so I guess so how do you know how many significant figures? Use your reason. And so my answer is negative 50. I expected it to be a little bit bigger number than that, but I guess I didn't really take into account that this term would end up, that my entropy would end up being negative, because I guess I just was looking at the numbers and I didn't really look at the chemistry of my equation, and so that's bad on me. I went from the example that I used before where I have two reactants that combine to make one product. Obviously entropy is decreasing there because we have more order, and so I don't know why I expected it to be positive, but not using me noodle. But the overall reaction is indeed spontaneous. How did that work out? Okay, so for number 2, we're asked to calculate the standard molar entropy change for each of the following reactions. And so for this reaction, you're going to need to calculate delta S for A, for B, and for C, and then just verify that when you add them together, you get the last reaction. So that's more of what we had been doing last time, calculating entropy. And then I just want to make sure, and I really didn't want to get to that today. Well, we might as well do it. For numbers 5 and 6 on the back page, you're going to need to know this equation. Okay, so what is this? This is another way of calculating Gibbs free energy where you're comparing whether or not a reaction will be spontaneous thermodynamically. You're comparing that with K, which is the equilibrium constant. So the greater the equilibrium constant, the more your reaction will go to completion. And so if you have this pretended reaction, if K is large, so in other words, if K is much greater than 1, you will have, at equilibrium, you'll have mostly all products because your reactants will be used up to form products. And so this is a little bit of a different way of seeing whether or not your reaction is thermodynamically favorable based on its tendency to go to completion or not. There are just some reactions that, while we know that they will produce a little bit of product, they just don't, not all of the reactants turn into products. think probably a good real life example of that is that gold doesn't really tarnish. We know that it does a little bit, like every tiny amount of gold atoms will form a bit of rust, but you never really see gold jewelry that needs to be polished because it happens on such a small scale compared to like silver jewelry, for example, or like what you know is not gold jewelry, like if it's like gold plated or like nickel or whatever, because those reactions occur so much more. Okay, so talking about this like in terms of the math then, R is the ideal gas law constant. And I believe that you need to use the R value associated with the SI unit, which is the one R equals 8.31. But that I'm using that from my memory. Let me just make sure. Yep, that's right. The SI unit for pressure is not ATMs. T is temperature, but it also must be measured in Kelvin. And then ln is the natural log. Have you guys gotten to natural logs in math at all? A little bit maybe?
Yeah.
You don't need to know what it is. I'm not going to ask you to like graph the function or anything like that. You just need to know how to manipulate the equation if you're solving for K. So if you know the equilibrium constant, you can do this math because this is always a constant. It's always 8.314. Temperature should be given to you in your problem someplace. And then if you know K, you can easily calculate delta G by typing into your calculator. But if you don't know K, you can find it. The way that you would do that, though, involves a little bit of mathing. So to solve for K, I would have to get K by itself. So I'm going to divide both sides of my equation by negative RT, and that'll leave me with ln of K on the right side. Do you know how to undo natural log? Like you undo multiplying by dividing. Do you know how to undo natural log? No?
Is it exponential?
You take it, like, you raise everything to the E. Yep. Okay, so then that would mean that you would have E, which is a button on your calculator. It is a number, but most usefully it's a button on your calculator. And so K is equal to E to the negative delta G divided by RT. You got to be careful when you're putting this into your calculator, though, because order of operations is a thing you have to teach your calculator to do. So just be careful on that. It's not hard to use your calculator. In fact, if you forget what to do, it is, if you look at your calc and you see, if you find the natural log button, pressing second will undo that. In the same way that 10 to the x is the undoing of log, e to the x is the undoing of the natural log. And so it's just a matter of typing it into your calculator. So remember that if delta G is positive, that means that it is non-spontaneous. The way to make that happen is for K to be less than 1. So in other words, a small number. Because not a lot of product, it's not thermodynamically favorable to produce products. If G is negative, it'll be spontaneous, and that likely means that K is greater than 1. So another little box for you to remember and memorize, and if you can manage that, that'll really help you answering questions on your AP test. Sometimes it's not a matter of like knowing the numerical value. Sometimes if you know these properties and how they're interrelated, you don't even have to do the actual math. You can competently answer, especially an MCQ question, without having to actually type anything in. Which, when you're only given a minute and a half on average for all of them questions, can be a dub. Okay, there's only one sheet of paper here, and I would like it if you could have it done, please, for me by next class so that we can move on. We'll be talking about the Nernst equation on Thursday, and then we are really getting to the end of our content. So that'll be a good thing to help us get ready for the test. Yay.